Let us continue fajans rule. Let us continue fajans rule. Now we will take anions. We will take anions is F minus. We will take F minus electronic configuration. If you see nucleus 1s2, 2s2, 2p6, 2s2, 2p6. This is F minus 1s2, 2s2, 2p6 is F minus. Then we will take Cl minus. Cl minus electronic configuration. First we have written nucleus, then we will write 1s2, then we are writing 2s2, 2p6, 2s2, 2p6 we are writing, then we are writing 3s2, 3p6, 3s2, 3p6 we are written. This is what in the sense Cl minus. Now if we see the size, if we see size of this one is small, size of this one is high. Since the size is small, electron cloud is tightly bounded by the nucleus. Here electron cloud is loosely bounded by the nucleus. So due to cationic pull of this anion electron cloud, this electron cloud easily distorts. This electron cloud, extent of this electron cloud distorting towards cation, distorting towards cation. How it will be there means that will be having lesser tendency when compared to Cl minus. Here lesser tendency, but here extent of electron cloud distorting towards cation is high. That means cation is pulling anion electron cloud. Cation is pulling anion electron cloud. Therefore, anion electron cloud is distorting towards cation, moving towards cation. Here, since electron cloud is tightly bounded, distorting of this electron cloud towards cation is less. Since the size is high, electron cloud is loosely bounded. Therefore, this electron cloud easily distorting towards cation cell. What is the meaning of that? That we will see. First, we will take a NaF. We will take Na plus F minus. Will take like this. Now, this is Na plus. It is nucleus Na plus electron cloud. It is the nucleus F minus electron cloud. Now we will assume that 100% ionic nature. Now it is assumption. What is the actual fact? Actual fact says what we will see. Na plus nucleus and Na plus electron cloud. Na plus electron cloud. Then F minus nucleus. This Na plus cation is pulling F minus anion electron cloud. Therefore, F minus anion electron cloud is distorting towards cation. Distorting. So this F minus anion electron cloud is distorted towards cation. Okay. Therefore, here we can say distortion of F minus electron cloud towards Na plus. Due to this distortion, that means distorted electron cloud. Distorted electron cloud is how much in the sense this much. This is a distorted electron cloud. Okay, this distorted electron cloud is shared by both Na plus and F minus. This distorted electron cloud is shared by both Na plus and F minus, we can say. Shared in the sense, what is that meaning? Covalent nature. Covalent nature. Okay. Therefore, since the electron cloud is going for sharing, covalent nature is there. Therefore, ionic nature is not 100%. Ionic nature is not 100%, we can say. So how much covalent nature is creating, that much ionic nature is reducing. How much covalent nature is creating, that much ionic nature is decreased, we can say. Okay. Now we can say here, this F minus electron cloud is tightly bonded. Cl minus electron cloud is strongly bonded. Therefore, here this electron cloud is slightly distorting towards cation, whereas this electron cloud highly distorting towards cation. Therefore, here electron cloud distortion is less. Therefore, sharing of electron cloud is less. Sharing of electron cloud with cation is less. Whereas here distortion is more. Therefore, sharing of electron cloud with cation is high. Since sharing is high, here we can say covalent nature is high. Since sharing is low, here we can say covalent nature is low, we can say. Therefore, here we can say, if size of anion is low, covalent nature is low. Size of anion is high, covalent nature is high. So what Fajans says, we will see. What is the Fajans rule? We will see. As per Fajans rule, as size of anion increases, percentage of covalent nature increases. This is Fajans rule. So as per Fajans rule, we can say that size of anion increasing in the sense percentage of covalent nature increases, we can say. Seriya? It is about anion. Sir. So when anion size increases, percentage of covalent nature increases, we are saying. Sir. In the Fajans rule, another point we will see. Now we will take different types of cations. Okay. Now we will take a fourth period. Fourth period we will take. In fourth period, what are the elements are there in the sense potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, gallium, germanium, and goes on. In this fourth period, we will take the element called potassium, we will take, and the element zinc we will take. Potassium electronic configuration, we will write potassium electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s, 3s2, 3p6 we have written, 4s1. So it is 10 plus 9, 19 electron. 19 is the atomic number for this potassium. So electronic configuration we have written. Now potassium comes under group 1A. Group 1A means this valence is 1. Therefore, it can show charge plus 1. That means it can donate 1 electron. Which electron it can donate in the sense this electron it will donate. Potassium will donate this electron. So the configuration is 2, 8, 8. It is the configuration of K plus. 2, 8, 8 in the sense it is what configuration means argon configuration. This is a argon configuration, we can say. The K plus configuration is argon configuration. So, next we will take a zinc. We will take zinc atomic number is 30. Electronic configuration is 2, 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. Therefore 18, 4s2. This is the electronic configuration of zinc. Zinc comes under group number 2b. Therefore its valence is 2. So it can donate 2 electrons. Therefore it can show plus 2 charge. Its electronic configuration is 2, 8, 18. 2 means 1s2, 8 means 2s2, 2p6, 18 means 3s2, 3p6, 3d10. 3s2, 3p6, 3d10. Okay. Now K plus is having noble gas configuration. K plus is having noble gas configuration. Noble gas configuration in the sense inert gas configuration, argon configuration it is having, therefore it is stable. Zn2 plus is not having inert gas configuration. Inert gas configuration in the sense this should be ns2np6. This should be ns2np6. Though it is not having inert gas configuration, this shell is this shell now this is the last shell for Zn2 plus. This last shell is completely filled. Therefore, its stability is just like a inert gas configuration. Therefore, we can say it is called a pseudo inert gas configuration. So, pseudo inert gas configuration means that the last shell will have 18 electrons in the ionic form. In this ionic form, we are saying not in this zinc, in the ionic form. Okay, so pseudo inert gas configuration means for which you want to say for that last shell we have to see if the last shell is having 18 electrons, then we have to say pseudo inert gas configuration. Okay, so this is Zn2 plus, we are talking about Zn2 plus. This Zn2 plus last shell is having 18 electrons, therefore Zn2 plus is having pseudo inert gas configuration. But now K plus will see K plus last shell is having 8 electrons, therefore noble gas configuration. Inert gas configuration means last shell should have 8 electrons. Pseudo inert gas configuration means last shell should have 18 electrons. Zn2 plus last shell is having 18 electrons, therefore Zn2 plus comes under pseudo inert gas configuration. K plus last shell contains 8 electrons, therefore K plus comes under inert gas configuration. Okay, inert gas configuration in the sense stability will be high. Pseudo inert gas configuration means stability will be low on comparing of these two. On comparing these two, we can say this is having higher stability, this is having lower stability. Now, this K plus is having higher stability, therefore, this K plus is having higher stability, therefore, it is having less tendency. This K plus has a less tendency to pull anion electron cloud. Anion electron cloud. This Zn2 plus is having lesser stability, therefore Zn2 plus is having high tendency to pull anion electron cloud. Okay, anion electron cloud. That means this K plus is having less tendency to pull anion electron cloud, therefore its polarizing power will be low. This Zn2 plus is having higher tendency to pull the anion electron cloud, so for this polarizing power will be high. Therefore, polarizing power is less in the sense anion electron cloud distorting towards this cation lesser extent. Now we can say in the K plus towards K plus. Now polarizing power is less for K plus. Therefore, anion electron cloud distorting towards distorting towards uh, distorting towards K plus to less extent. Okay, because polarizing power of K plus is less, therefore. But Zn2 plus if you see polarizing power is high. Polarizing power is high in the sense then we can say anion electron cloud distorting towards Zn2 plus to more extent. We can say Zn2 plus in the sense here anion electron cloud distorting towards Zn2 plus to more extent. Okay, anion electron cloud distorting towards Zn2 plus to more extent we can say. Therefore, here distortion is less. Here we can say distortion is less. Therefore, percentage of colon nature is less. Here percentage of colon nature is less. Here distortion is more. Therefore, percentage of colon nature is high. Here distortion is more. Therefore percentage of colon nature is high. Here distortion is less, therefore percentage of colon nature is less. Okay, therefore if you see inert gas configuration, so K plus is having noble gas configuration, therefore percentage of colon nature is less for K plus compounds. Zn2 plus is having pseudo inert gas configuration, therefore percentage of coal and nature is high. Therefore inert gas configuration means percentage of coal and nature is less. Pseudo inert gas configuration means percentage of coal and nature is high. So conclusion we'll see. What is the conclusion of Fajans rule? We'll see. As per Fajans rule, what is the conclusion? Okay. One is as size of cation increases, percentage of coal and nature decreases. Then as size of anion increases, percentage of coal and nature increases. Then if cation is having noble gas configuration, cation is having noble gas configuration, have lesser percentage of coal and nature. If cation is having noble gas configuration, then in that compounds percentage of coal and nature will be less. If cation is having pseudo noble gas configuration, pseudo inert gas configuration, if cation is having pseudo inert gas configuration, then percentage of coal and nature will be high. This is about a Fajans rule. So if size of cation increases, percentage of coal and nature decreases. If size of anion increases, then percentage of coal and nature increases. If cation is having noble gas configuration, then percentage of coal and nature will be low. If cation is having pseudo inert gas configuration, then percentage of coal and nature will be high. Okay. So this coal and nature is low means we can say ionic nature will be high. Like this we can say. So sum of the percentages will be 100. That's all. So how much extent coal and nature is there? To that much extent less ionic nature will be there. If coal and nature increases, ionic nature decreases. In that way we have to say. Okay. So from this analysis we come to know that no compound is perfectly ionic. Similarly, no compound is perfectly covalent. That means ionic compound in the sense that is having 100% ionic nature, that is wrong. So now we will take ionic compound. Ionic compound in the sense for this ionic nature is 100%. That is incorrect. Ionic compound in the sense in that percentage of ionic nature is 100%. That is incorrect. Now covalent compound in the sense that percentage of covalent nature is 100%. That is incorrect. Percentage of covalent nature is 100%. That is incorrect. Covalent compound means in that percentage of covalent nature is 100%. That is incorrect. Therefore, what is the nature in the sense ionic compound means in that covalent nature will be there as well as ionic nature will be there. Both will be there. Even covalent compound also is having both nature. One is covalent nature will be there as well as ionic nature will be there. So whatever the compound you take, that will have covalent nature as well as ionic nature. So ionic compound contains ion. In the ionic compound, what is there means covalent nature will be present, ionic nature will be present. Covalent compound, if you take in that also covalent nature, ionic nature both will be present. But what is the difference in the sense percentage will be varied. That's all. Ionic compound in the sense ionic nature percentage will be less high, covalent nature percentage will be low. So ionic compound contains what nature means both covalent and ionic. For which percentage is high means ionic nature percentage is high when compared to covalent nature. Covalent compound means in that also covalent nature, ionic nature both will be there. Which nature high in the sense covalent nature will be high, ionic nature will be low. Okay. So even in the covalent compound, covalent nature, ionic nature both are present. But which nature is high means covalent nature is high, ionic nature is less. Like this you can say. So now we will take some compounds. We will take, suppose we are taking a LIF, LIF and NAF. In these two compounds, which nature is high? If we compare these two, in which case cold nature is high, in which case ionic nature is high, how to say? Now, if you see in this case, what is that means? LIF, F minus, NAF, Na plus, F minus. Anion is same, cation only is different. Anion is same, cation is different. So, here based on size of cations, you say the percentage of cold nature, that's all. So Na plus size is high when compared to Li plus. So size of cation here is more when compared to this. So this compound is having higher covalent nature when compared to this compound. Sorry, this compound is having lesser covalent nature when compared to this. Okay, see size of cation is high means percentage of covalent nature is low. As per that you say. So size of cation is high. Therefore, in this compound percentage of covalent nature is low. In this compound percentage of covalent nature is high. Okay, so that in the alkali metal halides, which one is having higher covalent nature means lithium compounds will have higher covalent nature when compared to other alkali metal compounds. So lithium compounds are having higher covalent nature. Why? Because lithium ion size is small when compared to other alkali metal ions. Therefore, lithium ion compounds will have higher covalent nature. Sorry. Now we will take now BeCl2, MgCl2 will take. BeCl2, MgCl2. In this beryllium oxidation number, beryllium charge is how much in the sense +2, magnesium charge is how much in the sense +2. Beryllium chloride, magnesium chloride you take. Now, beryllium and magnesium coming under one group only. Sir, beryllium, size of beryllium is small, size of beryllium is small, size of magnesium is high. Size of cation is high, therefore percentage of covalent nature is less here. Size of cation is low, therefore percentage of covalent nature is high. So beryllium chloride is having higher covalent nature when compared to magnesium chloride. Now we will take lithium and beryllium, LiF and now we will take a now we will take LiF and BeF2 will take. Li plus and Be plus 2. LiF cation is size is high, Be plus 2 cation size is small. Size of Li plus is high, therefore percentage of covalent nature is low. Size of Be2 plus is low, therefore percentage of covalent nature is high. Okay, here cation size we have to see. Li plus cation is a bigger size, Be plus 2 cation is smaller size. Therefore, this is having lower covalent nature, this is having higher covalent nature. Okay, in the same way if we change the anions also we can say. Therefore, remember that Fajans rule means size of cation, size of anion, noble gas configuration, inert pseudo inert gas configuration. Based on this, you say the percentage of covalent nature. If percentage of covalent nature is low, then percentage of ionic nature will be high. Okay, this is about what in the sense Fajans rule. Okay, next we will see about properties of covalent compounds, ionic compounds and coordinate covalent compounds. These properties we will see. First we will see about properties of ionic compounds. So first we are seeing about properties of ionic compounds we will see. So, properties of ionic compounds. This ionic compounds, how it is present in the crystal lattice. That is, no isolated discrete molecules exist in the crystal lattice. Okay, that is, no isolated discrete molecules exist in the crystal lattice. Okay, so in the properties of ionic compounds, see this point, that means isolation is not possible, discrete molecules not possible in the crystal lattice. So what is crystal? Crystal in the sense regular arrangement of particles. So what is crystal in the sense? Crystal means regular arrangement of particles. Regular arrangement of particles means then we have to say crystal. regular arrangement of particles. So, what is lattice? What is the meaning of lattice? That we'll see. Lattice in the sense a three-dimensional arrangement. Lattice gives a three-dimensional arrangement of constituent particles. Three-dimensional arrangement of constituent particles, that is called a lattice. So crystal lattice means a three-dimensional regular arrangement of constituent particles. That is called a what in the sense crystal lattice. Now, in the crystal lattice of ionic compound, discrete molecules we cannot say, isolated molecules we cannot say. Sir, how the crystal lattice will be there? That we'll see. Now we'll take a crystal lattice of sodium chloride. Now we are taking a crystal lattice of sodium chloride. We'll take. How crystal lattice of sodium chloride will be there means suppose it is Na plus means neighbor of this Cl minus will be there. Neighbor of this Na plus will be there. This neighbor Cl minus. Like this it will continue. Next year Cl minus. Next Na plus. Next Cl minus. Na plus. Here Na plus. Cl minus. Na plus Cl minus. It will continue in all the directions. All the directions it will continue. In this direction next Na plus will come. Here next Cl minus will come. Here next Na plus will come. It will continue like this. Here next Na plus will come. It will continue. Here Cl minus continuation. Here Na plus continuation. Here Cl minus continuation. Like this, it will continue in all the directions. That means three-dimensionally it will continue. Three-dimensionally we have to see. Here we have given two-dimensionally, but three-dimensionally we have to see. That means over this Na plus Cl minus will come. Over this Cl minus Na plus will come. Like this. Like this, three-dimensional regular arrangement of constituent particles is called a crystal lattice, we can say. So, now if we take this Na plus, this Na plus is this Na plus. For this nearest neighbor is this Cl minus. Next, this is one Cl minus, second Cl minus, third Cl minus, fourth Cl minus. Above this Na plus one Cl minus, below this Na plus one Cl minus. So this Na plus is surrounded by, for this Na plus nearest neighbors, how much means 6 Cl minus ions. For this Cl minus we'll see. For this Cl minus nearest neighbor is Na plus, this Na plus, this Na plus, this Na plus, above one Na plus, below one Na plus. So for this Cl minus, how many Na plus ions are nearest neighbors in the sense 6 Na plus ions. So for this Cl minus nearest neighbors, for this Cl minus nearest neighbors, how many means 6 Na plus ions we can say for this Cl minus. Therefore, how do we say then? What? How do we say that here discrete molecule? Here discrete molecule is NaCl. Is it called discrete molecule? How do we say isolated molecule? Isolated molecule is NaCl. How do we say this? Is it correct or wrong? Sorry, whether it is correct or wrong, first we will discuss what in the sense. In order to discuss this, first we will see in intermolecular forces. We will see regarding that. We will see. Then we will come to this case. Then we can understand this one. Okay. Therefore, before going to intermolecular forces of attraction, we will discuss some other concepts also. Sorry. Now we will take a. Now we will go for the molecule. The molecule is called what is the sense SO3 2 minus we will take. This SO3 2 minus we can give as sulfur. This sulfur valency shell is having 6 electrons because it is coming in a 6A group. That 6 electrons I will give like this. 6 electrons we have given. 3 oxygen atoms are there. The 3 oxygen atoms we will write. So 1 oxygen, second oxygen, third oxygen. Like this we have written. Then this minus 1 charge. Here minus 2 is there. That minus 2 will give us minus 1 charges for this oxygen minus 1, for this oxygen minus 1. Then we will give electrons. This valency shell contains 6 electrons. That 6 electrons will write 6 dots. This valency shell contains 7 electrons, therefore 7 dots will give 7 dots. This valency shell also contains 7 electrons, therefore 7 dots will write. So here what bond means 1 bond, here 1 bond, here 2 bonds. Okay, this is what in the sense lone pair. So here one lone pair is present. One lone pair is present. So in this SO3 2 minus, this is what in the sense a double bond. This is what in the sense single bond. This is what in the sense single bond. So one double bond is present and two single bonds present. Sorry. What is the hybridization of sulfur in the sense? What is the hybridization of sulfur? We'll see. Hybridization of sulfur in the sense here how many sigma bonds, pi bonds, lone pair is there, that we'll see. Then only we can say hybridization. Here 3 sigma bonds are there, 1 pi bond is there, 1 lone pair is there in the sulfur. 3 sigma bonds, 1 pi bond, 1 lone pair. Pi bond is not explained by hybridization, therefore here 3 sigma bonds, 1 lone pair will take, therefore 4 in the sense hybridization is sp3. So hybridization sp3, hybridization is sp3. Okay. Hybridization sp3 in the sense, one possibility what in the sense tetrahedral shape, next possibility is a trigonal pyramid, next possibility is angular. In that which category it comes in the sense 3 sigma bonds and 1 lone pair means trigonal pyramid. Therefore shape of this is pyramid. So hybridization explains what is the shape of this species. Next we will see regarding bond length. Regarding bond length, as per hybridization, how many bond lengths will be there means this double bond will have 1 bond length, single bond will have 1 bond length. This single bond will have same bond lengths. This double bond will have different bond length. So double bond will have 1 bond length, single bond will have 1 bond length. Therefore, this SO3 2 minus will have 2 bond lengths. This SO3 2 minus will have 2 bond lengths. That is as per hybridization. That means as per this structure we are predicting 2 bond lengths. What does experiment says? Experiment says that only 1 bond length. Experiment says only 1 bond length. So as per experiment, number of bond lengths will be only 1 in the sense all these 3 bonds have similar nature. If all the 3 bonds will have similar nature, then only we can say only 1 bond length, isn't it? If this bond, this bond, this bond, this bond, all the 3 bonds should have same nature, then only we can say only 1 bond. So hybridization is unable to explain that fact. Hybridization is unable to explain this experimental result. Therefore, in the valency bond theory, another concept is introduced. That concept is called what in the sense resonance. That concept is called resonance. Okay. So resonance is the concept introduced in the valency bond theory in order to explain some more experimental facts. In the valence bond theory, first concept introduced is pure orbital overlapping concept that explained some of the molecules. Then hybridization is introduced. That hybridization is explained some of the experimental facts about molecules. Next, resonance. This resonance explains some more concepts about some more experimental facts about the covalent compounds. Okay, so now what is resonance? That we will see. Now, in the resonance, in the sense, what resonance is in the sense, first we have to write Lewis dot structure for the given species. Then Lewis dot structure. This is the Lewis dot structure for the Lewis dot structure is this one. It is called Lewis dot structure. Then in the resonance it says that how many possible Lewis dot structures possible for a given species, that many Lewis dot structures we have to write. So in the resonance, first what we have to do in the sense, we have to write the possible number of Lewis dot structures. Possible number of Lewis dot structures we have to write for the given species. So now we will take one of the species called what in the sense ozone. We will take ozone is the one of the species. For ozone, what is the formula in the sense? In ozone molecule, 3 oxygen atoms are there. So what is the Lewis dot structure for this ozone, that we will see. Lewis dot structure for ozone. Okay. For that case, ozone molecule contains 3 oxygen atoms. Those that 3 oxygen atoms will write. Now, for one oxygen atom, configuration is what means helium 2s2 2p4, that will write 2s2 2p4, 2s2 2p4. Another oxygen atom we will take, another oxygen atom, that configuration is what means helium, then 2s2 2p4, 2s2 2p4, that we have written for another oxygen atom. We will take another oxygen atom. For that another oxygen atom configuration is helium 2s2 2p4. 3 oxygen atoms we have written. We are writing this oxygen atom 2p4 as like this. We are violated what rule? In the sense Un's rule is violated. We violated Un's rule. Sorry. Now, this ozone molecule contains 3 oxygen atoms. Those 3 oxygen atoms electronic configuration we have written. Now we will write bonding. We will go for bonding. This oxygen unpaired p electron, this oxygen unpaired electron. This oxygen unpaired electron, this oxygen unpaired electron go for sigma bonding. This oxygen unpaired electron, this oxygen unpaired electron go for pi bonding. Next, this oxygen electron pair and this oxygen vacant orbital go for dative bonding. Go for dative bonding. This oxygen electron pair and this oxygen vacant orbital go for dative bonding. Therefore, we will go for hybridization. Now, in this oxygen, this oxygen is making how many bonds with this oxygen? Means 1 sigma 1 pi. And this oxygen is making 1 sigma bond, that is called dative bond with this oxygen. Shall we say dative bond is always sigma bond? No. Dative bond, even pi bond also possible. Dative bond we can say even pi bond also. But here between this oxygen atom and this oxygen atom only one bond means single bond means sigma bond. In that sense we said. Sir, this oxygen atom is is contributing this electron pair to this oxygen atom and making dative bond, that is sigma. So for this oxygen atom is making how many sigma bonds? Means 1 sigma here, 2 sigma bonds, 1 pi bond, and this oxygen atom is having this electron pair as a lone pair. So in this oxygen atom, 1 lone pair is there and 2 sigma bonds are there, 1 pi bond is there. So 1 lone pair and 2 sigma bonds, in the sense hybridization is what? sp2 hybridization. Therefore, this oxygen is going for sp2 hybridization. So oxygen goes for sp2 hybridization. That 3 sp2 hybrid orbitals will write. 3 sp2 hybrid orbitals will write. And 1 pure orbital will be there. 1 pure 2p orbital will be there. Okay. Now this oxygen valence shell is having 6 electrons. Those 6 electrons will write like this. 6 electrons we have written like this. Okay. This is one oxygen atom. So for one oxygen atom, we have written like this. Now we will see this sp2. Now this sp2 is what? In the sense lone pair. This sp2 is what? In the sense lone pair. Now this sp2 electron pair and this vacant orbital go for dative bonding. This dative bonding is sigma. This sp2 unpaired electron, this p unpaired electron go for sigma bonding. This unpaired electron of 2p, this unpaired electron of 2p goes for sigma bonding. Okay. Therefore, how the ozone structure will be there, we'll see. In this ozone, 3 oxygen atoms are there. 3 oxygen atoms will write like this. Central oxygen atom is having 1 lone pair in sp2 orbital. Lone pair in sp2 orbital. Then this oxygen atom is making 1 sigma bond with this oxygen atom and a pi bond with this oxygen atom. So 1 sigma bond, 1 pi bond. That means a double bond. Then this oxygen atom is making dative bond with this oxygen atom. A dative bond it makes. This is a ozone Lewis dot structure. Lewis dot structure, in the sense we have to give dots.